I'm Carolyn Matl, a PhD student at UC Berkeley and Ruzena Bajcsy's Heart Lab. This work was done in collaboration with Yashraj, Narang, Dieter Fox, and Fabio Ramos from NVIDIA's Seattle Robotics Lab. In this presentation, I'll be presenting STReSSD, a novel framework that uses sound to bridge the simulation to reality gap for stochastic dynamics, demonstrated for the canonical case of a bouncing ball. Sound is an information-rich medium that captures dynamic physical events. When objects collide with each other, they create sounding vibrations that can help a robot discern several important properties of those objects, including their material and size. In this work, we use sound to extract the times and positions of collision events for the stochastic dynamic system of a bouncing ball. We use these simple features of sound in our presented framework to automatically calibrate simulations of the bouncing ball. Through this, we show that audio perception is an effective sensory modality for bridging the gap between simulation and reality, and it's well suited for real-time dynamic scenarios due to its intrinsic high frequency and low dimensional form. In addition to this contribution, we observed from literature that modeling these collision events can be highly complex, since surface asperities on the surface of the object or ground may cause the motion of the object to be perturbed in an unexpected way. To account for this stochasticity, we introduce a new collision noise model into our simulator, and this model is learned from real audio observations. Finally, we conduct 2 robotic experiments to first demonstrate the predictability of the calibrated simulator in new scenarios, and then, combined with auditory feedback, to achieve reactive control in a vision-free robotic ball tracking task. We determined that the key material parameters to capture realistic ball dynamics in simulation are the coefficient of restitution, or E, which quantifies the energy dissipation of the ball upon collision, as well as the noise parameter kappa, which is the concentration parameter associated with a Gaussian on a sphere, otherwise known as the von Mises-Fisher distribution on a 2-sphere. We base our collision noise model off of this distribution. The smaller kappa is, the greater the perturbations are at every collision. Let's label these simulation parameters E and kappa as the vector theta. The information that we seek to observe from the collision sounds of a ball and table are thus associated with the temporal and positional features of each collision. We can extract the times and positions of the ball collisions by using 3 microphones positioned as so. Through physical reasoning, we hypothesized that these features would directly correspond to the parameters of interest. Let's define these features as the vector x. Given that we've defined our parameters theta, which we would like to learn, and our observation features x, which we will observe from real data, it would be valuable if we could find the posterior distribution of theta given x using a likelihood function L. However, because this likelihood function is defined implicitly by the simulator, it's difficult to evaluate, so we choose to use a likelihood-free inference approach, called BayesSim, to approximate the posterior of parameters given real observations. BayesSim directly computes a conditional density function by learning from pairs of parameters and summary statistics. These pairs are generated by independently sampling parameters from a physically based prior distribution and then forward simulating each sample. The posterior is then parametrically approximated using the learned conditional density and x super r, the extracted features of a real audio observation. This posterior is then sampled for every new simulation instance of that bouncing ball. Using the STReSSD framework, we were able to automatically calibrate the simulator for different contact scenarios between the ball and the table, including a ping pong ball bouncing on 2 different surfaces and a tennis ball and moon ball bouncing on a table. The calibrated simulators were shown to be effective in predicting the dynamics of the ball in a new scenario. The goal of this new task was to predict the success rate of bouncing the ball into a fixed cup from a specific position. The real experimental setup was replicated in simulation, and the predicted success rates in simulation matched closely with the real-life success rates. In addition to making open-loop predictions of ball dynamics, the calibrated simulators were used to learn a dynamics model to predict future bounce positions of the ball. This dynamics model was used in real time to track a ball in order to deflect it, using only sound as its sensory modality. We showed that incorporating our model of collision noise improved the robot's ability to complete this task. In summary, we demonstrate that audio can be a powerful sensing modality for tuning stochastic simulators and for guiding a robot in a highly dynamic task. Please see our paper for more details of the STReSSD framework and experimental results. And thank you for your interest in our work.